Hi everyone, my name is Abby Tescher and my capstone project was writing a literature review of the synthesis of benzothiazole derivatives with optical properties and use in organic light emitting diodes or OLEDs applications. So my project objective was to write a literature review outlining the synthesis methods of these benzothiazoles and their potential applications in OLEDs, with a goal of creating a manuscript for publication. After beginning this project, I realized the amount of work that goes into creating a manuscript, and it can be extremely challenging. However, my main journal of interest, if I had gotten that far, was Dyes and Pigments because it emphasizes on the chemistry behind optical properties, has a broader range of published materials, and especially on benzothiazoles in the past year. So my writing process began with a lot of research focusing on recent benzothiazole and OLEDs reviews to gain a better understanding of the organization in the format of current review papers. It began broadly by gaining background knowledge on OLEDs devices, desired properties and requirements of efficient lighting materials, and reading what has been previously accomplished in the past. In addition, there are many research papers on the optical properties of benzothiazole-based compounds that have been synthesized, noting the role in general that the heterocycles play in phosphorescent and fluorescent emission. I began organizing research articles by categories of reviews, synthesis approaches, as well as reported successes of benzothiazoles used in current materials. The organization focused down to the synthesis heteroatom and non-heteroatom benzothiazole derivatives in order to look into the possible donors for the donor pi acceptor structure that I began to focus on, and then the end with the conclusion and note on how the review will be useful for future work in synthesizing new benzothiazole derivatives. So some background information on OLEDs. This technology utilizes thin films of organic materials placed in an emissive and conductive layer between two conductors and allows the electron hole pairs to combine at the interface of the two layers. This combination moves an electron from the lowest unoccupied molecular orbital to the emissive layer of the highest occupied molecular orbital in the conduction layer, promoting electroluminescence, a process in which this radiative recombination of injected electron hole pairs occurs in a solid film. The figure on the bottom shows the composition of an OLED device stacked with an anode that is required to inject holes into the hole transport layer, while electrons are injected from the cathode into the electron transport layer, causing dyes in the emission layer to emit light. So parameters such as high external quantum efficiency, long lifetimes, reduced quenching effects, emission wavelengths covering the entire visible spectrum, and HOMO-LUMO levels permitting good charge injection, as well as chemical stability of the host material, are critical for manufacturing devices that can be commercially used in display technology. So therefore, only a limited number of suitable materials have been successful in OLEDs applications, especially for blue and white light. Many efficient optical materials have been push-pull chromophores that are based on an electron donor and an electron acceptor connected to each other by means of a pi-conjugated spacer known as push-pull system. And this donor-acceptor interaction is referred to as intramolecular charge transfer, or ICT. And due to the deficiency of electron density on the carbon ring atoms, the thiazole heterocycle acts as an electron withdrawing group and as an acceptor that is enhanced by the interaction with donor compounds. So benzothiazoles act as their acceptor, and carbazole, triphenylamine, thiophene, boron, and fluorine groups are examples I researched as donors. In addition, the pi spacers have large effects on the molecular properties. So some examples of previously reported spacers are ethylene, butylene, thiophenes, and phenyl groups. So for instance, phenyl-based spacers have resulted in reported blue shifts, while the spacer length has shown red shift effects in emission with thiophenes, and this was due to their planar conjugated structures. And the figure shown here is an outline of the donor pi acceptor system that I focused on in my project. And an important approach to improve OLED's performance is to develop new, highly efficient host materials while maintaining desirable photoelectric properties that avoid common OLED problems such as quenching and efficiency roll-offs. So heterocyclic molecules have brought much attention for their application in OLEDs due to their strong electron donating and withdrawing capabilities, better thermal and chemical stability, and excellent photochemical properties. And of the heterocycles, benzothiazoles are bicyclic heterocyclic aromatic molecules with electron-rich sulfur and nitrogen atoms. They act as a weak base formed in the benzene ring with the 4 and 5 positions for the thiazole rings. They are interest for OLEDs due to them being known to exhibit strong luminescence in solutions and in the solid state. while also covering a wide spectral range. The figure below represents benzothiazole as an asymmetrical molecule because it possesses electron withdrawing and electron donating groups on different positions. The virtual dipole between the electron deficient site and the benzene ring, the electron rich site, is oriented to facilitate the internal charge transfer within the molecule. So here I listed some examples of my synthesis research grouped by the donor components of benzothiazole compounds and noted some of the photochemical properties found in the benzothiazole containing molecules reported in literature. So carbazole is often used as the electron donating moiety in the non-doped OLED synthesis, and when paired up with the benzothiazole as the acceptor, fluorescent emitters have been developed. The research listed outlines Suzuki coupling reactions and mixtures of common benzothiazole synthesis of aromatic aldehydes and 2-aminothiophenols. And for example, the electron transporting benzothiazole and hole transporting carbazole moieties reported deep blue emission in solid and strong deep blue emission in solution with excellent fluorescent quantum yield with good thermal stability. And for the next donor, triphenylamine containing benzothiazole molecules have been synthesized by similar methods as well that I just listed, as well as metal catalyzed cross-coupling reactions. And in these reports, change of substituents were often shown to affect the solid state behavior, and increasing conjugation lengths also aided color tunability of these compounds from blue to green emission. And with thiophenes as a donor, it was shown to create better performance for lighting outputs in tested OLED materials, and redshifts were commonly observed in spectral analyses. And reported synthesis of benzothiazoles containing thiophene donor groups were achieved by reactions such as microwave-assisted synthesis, as well as acid-catalyzed cyclization reactions. And finally, I listed some of the literature found for boron complexes of benzothiazoles. They were obtained from base-catalyzed reaction conditions, and there's also another report explaining reacting with substituted 2-aminobenzothiazole and substituted benzaldehydes. And these papers reported boron complexes of 2 substituted benzothiazole phenols that led to deep bright blue and orange-red emitting materials. And interesting, researchers found the additive mixing of solutions as well as solid colors led to the production of white light emission, which is one of the major challenges for achieving OLED's full color displays. So I just wanted to include one example here of this is of the Suzuki coupling reaction of what it looks like for synthesizing benzothiazole derivatives. And this shows 2 bipolar blue emitters, the BFCZ and BFPCZ that were reported in 2019 by Song and researchers. So when starting materials were paired up with benzothiazoles as the acceptor, strong fluorescent emitters were developed. So many papers showing different methods were explored, and it was important to stay organized throughout this entire process. In the beginning, it was difficult to come up with an effective organization when I was considering the complexity of OLED materials and what would be the most effective route to display the synthesis of benzothiazole containing compounds for possible OLEDs applications. I found that utilizing a program such as Mendeley to keep all of my sources organized aided my process overall and helped me work alongside my advisor throughout this virtual experience. So here's an image showing how authors, journals, and dates of publications were easily grouped and displayed in the Mendeley program. In addition, it allowed me to insert my in-text citations into a Word document that I share on Box with Dr. C for easy collaboration of this project. In conclusion, I gained a better understanding of research in general as I spent most of my time researching for this project and obtaining sources that I could use in my review. I found that struggling to find a clear focus for my topic initially led me to gaining a lot of new information that I would have never looked into if I didn't start broad, however, and then narrow my search. I really enjoyed learning about the challenges of creating new OLEDs materials that researchers are trying to overcome in order to synthesize new small molecules for manufacturing more efficient lighting applications. And although I did not get my literature review to the point of my initial objective of manuscript submission, I enjoyed pushing my research interests and creating something that could be useful for future lab work on synthesizing benzothiazole derivatives for optical properties. So future projects may be able to reference the work Dr. C and I put together in order to synthesize benzothiazole derivatives for their optical properties. This could entail experimenting with different donor compounds to work on optimizing those properties based on their structure and different substituent effects used for tuning emission wavelengths, as well as stability in different materials. Thank you for listening, and I also just wanted to acknowledge Dr. Shakina for all of her help and mentoring this year throughout my entire capstone project, as well as all of the faculty and staff in the Pacific University Chemistry Department. It was really fun to go through all my research and be able to apply a wide array of things I've learned in all of my different classes to my project this year. And as always, my students and peers and my friends, thank you so much.